Greetings to all. So today we will be dealing with the energy absorbing materials. So we will look into how the behavior of the energy absorbing materials, when to choose them, what type of energy absorbing materials to choose, and their implications and the significance that they play in our day to day life. So this is a illustration of the vehicle accidents that are occurring across our nation. So on the left hand side we see the state-wise rate of occurrence of the accidental injuries in our country. Okay. And on the right hand side we see the expenditure that is occurred during the accidental injuries. In our day to day life, we either by ourselves or by some next of our kin or some of our loved ones has been under an accident, okay, sometime in his life, okay. And the amount of safety that is inbuilt into the vehicle that is being driven and the safety measures that are being implemented in the road makes the difference between the life and death scenarios. Also, if one survives, then one has to undergo the different type of surgeries or anything, okay, and that also accounts for a huge expenditure, okay. So our job is to make our roads safer, okay. The vehicles that in which we are driving has to be safe for the inhabitants, the occupants that are inside that, and it has to also save the inhabitants from any external threat, okay. So that safety measures needs to be implemented in the vehicle as well as the surrounding material. So in this case, what we are trying to achieve is a safety measure, okay, that we deal in our day to day life during an event, okay. So this type of event is called an impact event, okay. So basically we are looking into an example, okay, of an impact type of event in which we have to devise the safety measures, okay. So let us take the example of a car, okay. The normal weight of the car is around 2 tons, okay, means 2000 kgs, okay. And in case of highways, okay, the speed, the driving speed, velocity ranges from 80 kilometer per hour to around 120 kilometer per hour, okay. So in essence, we are driving a small projectile, okay, with a low velocity, okay. So this is a 2-ton projectile having a mass of 2 ton driven at a velocity of around 80 to 120 kilometer per hour, okay. And if this is going to hit another car, okay, or even if it is going to hit a rigid bars, okay, like a guardrails, okay. Guardrails are nothing but a strip of steel bars, okay, that are put across the boundary of a road to protect the inhabitants from veering off, hitting some other body, falling on a cliff, okay. So even if this body is hit or this car is going to hit some other body, there will be a massive amount of transfer of the momentum, massive amount of transfer of the energy, and the force between these two cars will be very high, as we have seen during the contact event, and it might cause severe injuries to the inhabitants inside it, okay. So in order to protect it, we have to devise some sort of safety measures, okay. So a simple representation of this event is shown here, okay. So here we are dealing with a stationary object, okay, a rigid mass, okay. The car is traveling with a velocity v, okay, let us say it has a mass m, okay, and the system on which it is going to hit, okay, as we have seen earlier, this can be represented with a spring constant k and a phase here, okay. So this is nothing but a spring mass system, okay, it has a mass m and a stiffness k, okay. So what happens, the car is going to accelerate, the body is going to accelerate towards the spring mass system or towards any let us say this represents a guardrail, okay. So this is going to accelerate towards the guardrail. So guardrail has an engaged mass and the stiffness, and after the hitting the guardrail, it is going to deaccelerate in the other event, okay. So what happens to this car during this impact event will be determined by the signature of the stiffness and the mass of this impacted body, okay. So we need to devise this guardrail, okay, so that the minimum damage occurs to our moving vehicle, and the people sitting inside it are safe and sound. Okay. Earlier we were dealing with a very specific case of the vehicle impact. Okay. So, the applications we can see, the key systems are vehicle comfort zones, the guardrails as an energy absorbers, the protective helmets. Okay. So, these are the some of the things, okay, that during a vehicle movement comes into pictures. Okay. The helmets, the guardrails, the vehicle comfort zones. Okay. So, the design requirement may vary depending upon what is being designed. So, it has a constant reactive force, some sort of energy threshold that we will be talking in detail later on. Again, stroke, the structural length, and the stable deformation pattern. Okay. So, these things we will are the quantitative criteria that are used to design the energy absorbing materials. Okay. Basically, what this will do is that they will try to give how efficient, okay, or how reliable the energy absorbing system is in place. Okay. So, coming about the material and structural considerations. So, there is a term used that is called the specific energy absorptions. Okay. So, in the context design of the energy absorbing systems, okay, this term is being used. Okay. What is this term? So, this term is nothing but it is a performance metric. Okay. So, using this term, okay, using this value, we can judge between the two different types of energy absorbing system. Okay. It quantifies the energy absorbing capacity of a material per unit mass. Okay. So, this value is typically expressed in terms of joules. Okay. So, this is nothing but it is the total energy absorbed divided by the mass of the system. Okay. Okay. So, this gives the efficiency of that particular material. Okay. So, if you see the steel, okay, the total energy absorbing capacity per unit mass of the structure of a steel is around 20 to 30, aluminum 40 to 60 and 50 to 80. Okay. So, higher this number, the good it is as a specific energy absorbing material, simply meaning that if I use steel, okay, I will be requiring more mass of the steel, okay, to achieve the same energy absorbing capacity. If I use FRP, I will be using less mass of the material to absorb the same amount of energy absorbing capacity. Okay. So, that is why if the SEA is more, the specific energy absorption is more, the material is quantified as a good material or a better material for the energy absorption. Okay. Okay. So, now we deal into some of the basic equations, okay, for quantifying the material absorbing capacity. So, E is the input, the total energy that goes into the system. As an output, the kinetic energy comes into picture, the strain energy comes into the picture, and the energy dissipated comes into the picture. Okay. So, this relationship gives the behavior of the material in a dynamic event. Okay. This is the material behavior during a dynamic event. Okay. So, here epsilon dot is nothing but the dynamic strain rate change. Okay. So, we will be dealing with this thing in detail. Okay. So, this is the empirical formula to account for the strain rate sensitivity of the material under dynamic loading. Often one of the used formulation is the Copper-Simmons model. Okay. So, what it is telling us that if we have a material, okay, and we are trying to measure the stress strain behavior of the material, okay, and we are going to, let us say we are testing a bar, okay, at a very slow rate, okay, then the behavior of the material will be, let us say if it is something like this. Okay. If we increase the rate of the loading, okay, if the rate of, let us say this is for a very low rate of loading. Okay. So, the force is being applied at a very low rate. Okay. This is, let us say F1. Okay. So, corresponding to that, the stress strain behavior will be something like this. If I am trying to introduce the force at a very high speed, okay, if I keep on increasing the force at a very high speed, okay, if I increase it F2, F3, what is going to happen is that the stress strain behavior will be looking something like this. So, this is F1, this is F2, this is F3. F1, F2, F3 denotes the rate of loading. Okay. Okay. So, there are two significant points to see out here. The value of the stress is increasing, okay, but the value of the strain is decreasing. It means that my material is becoming stiffer and stiffer, okay, but the ductility I am losing into the ductility side. Okay. So, in a given dynamic event, if the rate of loading is very fast, okay, so the material will become stiffer, okay, the value of the stress that it can undergo will be more, but it will lose the ductility also. Okay. So, this behavior is being represented here, okay, and one of the widely used model is called the Copper-Simons model. Okay. So, sigma d is the dynamic yield stress, sigma s is the static yield stress. Okay. So, the dynamic yield stress is written in terms of the static yield stress. Okay. So, static yield stress is nothing but this signature, okay, when the rate of loading is very low, and the dynamic is any other signature where the rate of loading is more than the dynamic loading. Okay. And epsilon is the applied strain rate. Okay. Epsilon deals with the rate of loading. Okay. So, as the rate of loading is increasing, the behavior of the material changes and it becomes more stiffer. Okay. G and Q are nothing but the material constant that are determined experimentally. Okay. So, the point here to remember is that the material behavior during a dynamic event is different than that of a static event. The material will become stiffer, it will harden. So, the stress and the Young's modulus will go up, okay, but it will lose in the strain and the ductility will come down. Okay. So, what we do normally is that we use the idealization of the material behavior. So, we use tensile tests to characterize the material. So, stress strain curve are being evaluated, and these idealized models, okay, normally in case of metals we use the elastic perfectly plastic, linear or power hardening models. Okay. If the plastic deformation is more, then we use rigid plastic models. Okay. So, elastic perfectly plastic is nothing but we use this type of models, okay, of the stress strain rate, and for a rigid, for large deformation we use this type of models. Okay. So, the typical equations, sigma is related to the strain Young's modulus, okay, sigma equals to y perfectly plastic and linear hardening. Okay. So, this type of material models are being used. Okay. So, the actual behavior might look something like this, okay, and this sometimes is implemented like this, or an idealization like this is being used. Okay. So, this is nothing but to why we are doing this. First, we are trying to get a very conservative estimate of the material behavior, and we are also trying to remove the kinks, okay, or the discontinuity associated with the material properties. So, we idealize it, okay, using elastic perfectly plastic or rigid plastic model, so that the analysis can be carried out. Okay. Moving ahead. So, yes, so this is the thing that we were describing earlier. So, this is the case of the idealized stress strain curves of material under tension. Okay. So, A is rigid, okay, this case rigid perfectly plastic one. Okay. So, this is used in case of large deformations. Okay. Next thing is the rigid linear hardening, okay, your hardening is occur, okay, and this is the power rate model. Okay. Instead of a linear model, we use some sort of power rate model. Okay. So, this signature we can see in case of Copper-Simons model also. So, here also some power law is being used. Okay. So, in the plastic deformation, the hinges will form, okay, and the plastic deformation will try to accumulate at the point of the hinges. Okay. So, this equations gives the behavior of the material, okay, for the elastic perfectly plastic beam, okay, where m is the applied moment, it is being normalized with me, that is the elastic moment capacity. Elastic moment capacity is nothing but the maximum moment that it can undergo before yielding occurs. K is the curvature, K is the elastic curvature, and theta is the rotation. Okay. So, the same thing are being used, only thing is that we are evaluating the material at the point of the plastic hinge formations. Okay. So, again continuing into the behavior. Okay. So, the elastic perfectly plastic behavior, we can use a spring and a friction model. Rigid perfectly plastic material, a friction model can be used. Okay. A plastic hinge, a mechanical hinge with a critical moment can be used. Okay. So, the validity of this approximations, error of rigid plastic model decreases with increasing energy input. Okay. As more energy is input into the system, the error associated with the rigid plastic model decreases. So, we will see these things when we are dealing with the equations and we are dealing with the design of a particular system. So, limit state. Okay. During a limit state, the structure is going to deform plastically. The definition of the limit state in this case becomes zone where the structure is deforming at plastically, okay, at a constant rate. So, lower bound theorem, so it is nothing but a statically admissible stress fields, and it gives a lower bound for the collapse load. Okay. Upper bound theorem, a kinematically, first the lower bound theorem is statically admissible, the upper bound theorem is kinematically admissible. Okay. And the limit state remains between these things. Okay. So, some of the examples that we will be covering is the beam under bending and axial force. Okay. There is an interactive limit also, where the moment and the axial force both comes into picture. So, here we are seeing a beam under combined action. A beam is undergoing, normally what happens in a beam? Okay, there is an axial applied load, there is a vertical load applied and there is a moment, okay, and beam undergoes deformation like this. Okay. So, here we are dealing a case where the beam is undergoing deformation like this also in bending case, but there is an axial application of the load also. Okay. So, here what is going to happen is that when the beam starts, okay, it is under the elastic limit first. Okay. So, as the elastic limit increases, a point will be reached, okay, in the maximum strain profile where the elastic limit is reached. Okay. After that, the plastic zone is going to form, okay, and it is going to propagate through and through. Okay. Once it reaches the neutral axis, the fully plastic zone is being reached. Okay. So, here we say that a hinge formation has occurred. This is the point of the hinge formation where the entire cross section has reached its elastic limits. Okay. It is beyond undergone the elastic limit. Okay. So, this is the case. Okay. And in this case, we are examining both the application of the bending as well as the axial elongation. Okay. So, this is an interactive curve. Okay. So, this type of curves normally we deal when we are designing a column. Okay. So, in a column there is an application of the moment as well as an application of the axial force. Okay. So, this line is generally addressing the capacity of the moment, okay, to take care of the moment also and to take care of the axial load also. So, if the combination of the applied axial load and the applied moment is under this boundary, okay, the column is going to be under the limit state zone, and if it goes beyond, the limit state is breached. Okay. So, a beam subjected to bending moment and axial force. So, this was this case, and the stress profile across the thickness in the plastic state. So, this is the formation of the plastic state and the corresponding hinge formation, and this is the interactive limit curve, okay, in the MN plane. Basically, the capacity, this is the applied load versus the capacity plane. So, this is the limit state plane. So, if the loading combination is below this value, the thing will be under the limit state, and if this curve is breached, the limit state is said to be breached. So, we will look into a beam with bending moment M and an axial force N. Okay. We will try to draw the limit curve, okay, that is a parabolic curve, and a plastic hinge forms when the combination remains the limit curve. Okay. So, the total energy dissipation at the hinge will be a combination of the moment capacity and the axial capacity. So, effects of large deformation. So, large deformations alter equilibrium and the load paths. Okay. A collapsed load changes moving hinges force direction. So, a simple example can be a clamped beam indented by a rigid punch. Okay. So, if this is a clamped beam and if a rigid event occurs here, okay, that is the striker is rigid and it tries to punch down here. Okay. So, here a large deformation is going to occur. Okay. So, axial forces can enhance load carrying capacity. So, this is an interesting thing. Okay. So, we know that if a member is subjected to a triaxial state of stress, okay, the stress carrying capacity of the member is enhanced, okay, because the confinement adds up to the total stress that it can carry. Okay. So, sometimes one way to increase the carrying capacity of a member is to subject it to a triaxial state of stress. So, the effect of the dynamic loading, the stress wave propagation occurs as we have learnt earlier in the previous classes. So, the elastic waves and the plastic wave transverse through it, the inertia wave effects. Okay. So, the inertia affects the mass of the system, okay, it alters the deformation mechanism and the energy absorbing capacity. Dynamic versus static response, dynamic loads can change the efficiency of the system. Okay. So, as we have seen, in case of a static load, the stress strain behavior might look something like this, and in case of the dynamic loading, the stress strain behavior changes like this. Okay. Though the stress carrying capacity is increased, okay, but the ductility of the system is reduced. Okay. So, this some examples can be a free beam can sustain dynamic but not static load. Okay. So, this type of examples we will see in detail as we progress. Strain rate effect, the same thing that we were talking about right now. Here for a static type of event, okay, or the strain rate is very low, okay, strain rate is low, then the stress strain behaviors will look something like this, but as we increase it, okay, the stress will increase with the strain rate. You can see the stress is increasing with the strain rate, but the strain is going to go down. Okay. One way of this formulation is the Copper-Simmons model, but there are other many models associated with the different materials, okay, that exhibit or that try to mimic this stress strain behavior. So, this phenomena has to be considered for a crash on impact event, okay, because for a high dynamic loading type of event, the material behavior changes and we have to account for this change in the behavior. So, the material sensitivity affect the energy absorption predictions. Okay. So, this behavior has to be taken into account if we want to properly predict the energy absorbing capacity of any given material. Okay. So, fundamental mechanism, what happens when the energy absorbing materials, okay, comes into contact with the impact event. Okay. So, we will be looking into the reinforced concrete type of things. Okay. So, the energy absorption occurs through inelastic deformation. The major mode of the energy absorption is through in the inelastic deformations. So, there will be flexural yielding, there will be shear resistance, and there will be a fiber reinforcement effects. Okay. And these are critical for the seismic designs. Let us say a building that is designed for an seismic event, and the impact resistance, okay, like our median crash barriers, okay, the big crash barriers that we see, okay, in the middle of the road. Okay. So, their design is governed by this phenomenon. So, the key for performance factors, okay, the reinforcement design, the ratio and the arrangement matters. Okay. Let us say an barrier is designed, an RCC's barrier is designed like this, and a car is going to hit it like this, a car or a moving truck. Okay. So, the total behavior will be determined or will be also influenced by the amount of reinforcements present in the steel, okay, their ratio as well as the arrangement. Okay. Let us say we look into two cases. Okay. So, the ratio is nothing but the volume of the amount of steel present divided by the total volume of the given section. Okay. So, let us say here we say that this is 2%. Okay. So, we know that in the cross section there must be 2% of the steel with respect to the total cross section. Okay. But the distribution of this 2% also matters. Okay. If we just jam it, okay, all the 2% here, okay, then this thing might not be effective. So, there might be cases where we have to distribute this 2%, okay, equally amongst the cross section to make it more effective. So, in the RCC design, the reinforcement ratio as well as the arrangement matters. Okay. The amount of steel that is being put into the cross section and how this is being arranged. Okay. Whether this is being arranged everything at one place or it is being properly distributed across the cross section to get a more efficient design. Okay. So, this was this thing. So, cross sectional geometry, sometimes this geometry might be more efficient. Okay. Sometimes other T-shaped of geometry might be more efficient. Okay. So, the efficiency of the geometry comes into play. Why this geometry is important? Because we know that if we have a flexural member, okay, and it is being subjected to a vertically applied load. Okay. So, in this case, the top part will be in compression and bottom part will be in tension. Okay. So, concrete can take compression, but for the tension we have to engage the steel. Okay. So, we have to have our cross section, okay, so that the concrete part is more here, okay, because in this part the steel is going to play the picture. Okay. So, different type of geometry has to be evaluated. Okay. Concrete compressive strength, okay, the strength of this concrete will play a picture, maybe it is M30, M40. Okay. This means that the compressive strength of this thing is 40 megapascals. Okay. So, higher the grade of the concrete, the better the compressive strength is. But it has a catch. If we go into very high grade of concrete, okay, what is going to happen is that the strain associated with this concrete is again going to be lowered. Okay. So, let us say we have a threshold value, okay, of the strain, and let us say this is M30, meaning 30 MPa. So, in this type of grade of concrete, the strain value is within certain range. Okay. But if I increase it to a very high value, let us say M100, okay, what is going to happen is that the strain that it can undergo, okay, this decreases. Okay. So, though I have gained in terms of the stress, I have lost in terms of the strain. Okay. So, both value comes into picture. Okay. This value comes into picture due to the strength and this value comes into a picture due to the ductility. Okay. So, in the RCC design, a parity is sometimes needed, okay, for the stress versus the strain value. Okay. Inertia and the wave propagation effects also plays a picture here, and the loading condition, again static versus dynamic loading. The behavior of this material also changes with the dynamic loading. So, we have to see how much of dynamic loading is being implemented here. So, nowadays what is happening is that high density and high strength fibers, okay, are also used for the protection measures. Okay. So, in RCC design we use steel fibers. Okay. So, what it does is that it improves the residual flexural strength. Okay. So, there are some hybrid fibers made of steel and polypropylene. Okay. They exhibit a 30 to 50% toughness increase, and it enhances a better crack distribution. What is a crack distribution? In RCC what happens is, normal RCC, if a vertical applied load is there and the reinforcement will be at the bottom, okay, and when the load is being applied, what will happen is that small cracks are going to form like this. Okay. So, as the material goes further and further, the concrete at the bottom will exhibit this type of cracking. Okay. So, this steel fibers, they are distributed across the member. Okay. So, if this distribution is like this, they are going to arrest the propagation of this crack, and the behavior of the member will also be enhanced. Okay. So that's what it is being implied here, is that using the steel fibers, the crack distribution is also improved. Okay. So even with a very low dosage, let us say 0.%, 20% absorption increase is exhibited, and if we can increase to 1%, 40% absorption increase is exhibited. The only problem here is that the cost associated with this thing. Okay. Here we can see that doses are very low. Okay. So someone might say, why don't we use, let us say, 50% of the dosage. Okay. What will happen is that the cost of this system will shoot up very high. Okay. So we again have to maintain a balance between the cost associated and the increase in the absorption energy that we are going to see. Okay. So moving ahead. So again, one more improvement which is being exhibited nowadays is the high strength wire mesh. Okay. So previously what we saw the small steel fibers will be embedded into the members. Okay. So the next step is that instead of the steel fibers, okay, why not put a mesh, okay, that is made up of very high strength material. Okay. So this type of wire mesh are also being used. Okay. They are the strength of this material is very high. Normal steel is around your 500 MPa. This wire mesh strength runs more than 5000 MPa. Okay. So these are made up of very high density, high grade material. Okay. So they have a 40% higher energy absorption as compared to the conventional RCC. So the optimization parameters are wire mesh aspect ratio, okay, and the concrete strength. Okay. So using this type of materials, okay, we can get a very good increase in the absorption capacity. Applications, these things are used a lot in the blast resistant structures. Nowadays they are also being used in the impact resistant structures. Okay. The only drawback is the cost associated with this wire mesh. Okay. Since these things are made up of very high strength steel, okay, automatically the cost goes up. Okay. So the optimization of this wire mesh for the particular system has to be established, and then only we can put it, so that we get a very optimum increase. Okay. And the cost is also up to a certain extent only. Layered concrete, one way, we have seen the one way. Okay. In this way, the reinforcement, first the reinforcement was tried to put judiciously and as per the behavior, okay, across the section, on top of the section, the geometry was tried to improve. Okay. Then our fibers were being put, and after that the wire mesh was being used. Okay. So this type of different things was done to achieve an efficient absorption system. Okay. The other way is to play with the concrete also. Okay. Here we were playing with the reinforcement, now we can play with the concrete. Okay. We can make the concrete lightweight. Okay. We can make it layered concrete. Okay. We can put openings in the concrete, okay, make it like a waffle slab. Okay. So this way the inherent properties of the concrete can also be manipulated, okay, and adjusted, so that we can get more efficient performance from the concrete also. So in a mix and match between the enhancement of the reinforcement properties by using distribution, geometry, fibers, wire mesh, and concrete also, layered concrete, lightweight concrete, layered concrete, and openings in the concrete like a waffle slab, we can mix and match and get a proper efficient design. Okay. So small absorptions might just lead to the 16% reduction in the energy absorption. Okay. Large opening may be 80%. Okay. So here, okay, playing with all these properties, we can use an efficient design. Okay. So for an efficient design with less cost, okay, all these properties needs to be evaluated. So we will try to borrow some knowledge from the seismic design systems. Okay, so the seismic resistant buildings has been designed for a very long time. So some of the materials will try to borrow from that thing and apply in the impact and blast resistant field. So energy dissipation capacity. Okay, this is a term that is being widely used in the seismic resistant design of buildings, and this is nothing but the hysteresis area under the hysteresis slope. Okay, so what is being done is that a member is being taken, okay, and this is being given a force, okay, a force signature, where the forcing function with time, okay, behaves like this, okay, negative positive phase, simply meaning this is pulled up, okay, this material is being pulled up, and after that again it tries to traction back, okay, reaches 0 and again, okay. So this is the loading pattern of the forcing function, okay. And what happens is that the material starts here and it tries, this is the behavior of the material, okay. So this thing is called the hysteresis loop, okay, and the energy absorption capacity is been given as the area under this loop, okay. So this is how the energy absorption capacity of a particular material is being evaluated, okay. So the critical parameter that are addressed are the axial compression ratio, the cyclic loading history, this is the cyclic loading history, and the sectional shape. And we also deal with the failure mode priority, okay. Always a ductile failure mode is being prioritized over a brittle shear mode, okay. So the mode of failure is ductile flexure mode, that is tried to achieve, and this brittle shear failure mode is tried to minimize, okay. So this thing has been borrowed from the seismic design, okay. So I will stop here and will continue in the next time. Thank you.